Hello everybody. If you'll get some paper, and I'm just using ordinary printing paper, we're going to take a look today at how you graph half parabola projectile motion. We're going to look at position time graphs, velocity time graphs, and acceleration time graphs in both the vertical or y plane and the horizontal or x plane. Okay? All right, so I'm going to start I've split my paper in half, and one side is going to be for the x-plane motion, and the other is going to be for the y-plane motion. Okay? And I'm going to start by just simply creating some axes for us to work with. Okay, and I'm going to start with the position time, just so you know. Okay. All right. And we need to label. So you've got 0 for the time axis. And you've got for the x-axis and the x-plane, we'll have positive x and negative x, and we have positive y and negative y positions. Okay, now, for a object that travels a half parabola of projectile motion, like, say, a ball rolling straight off a table, we know that horizontally the motion is constant velocity. It doesn't change velocity as long as we have ideal conditions, no air resistance. Once it leaves the table, the only force acting on the projectile would be gravity, which is vertical and therefore independent of the horizontal motion. So let's think about an object that rolls off a table. In fact, right here, I'm just going to draw a little picture so we know what we're dealing with of a ball, and it's going to roll straight off the table and land somewhere out here on the floor. Okay, so let's start with the horizontal position when it leaves the table. If we take the horizontal position right here to be 0, we can start the ball right here. Okay? At 0, and we know that by the time it hits the ground, it will have traveled the range, and we'll call this x sub f. So we need to go, if we take to the right to be positive, we need to go up until we reach position x sub f, and it reaches x sub f in the hang time. The hang time. Okay, we call the time for the trip of a projectile the hang time. I'm not sure if I mentioned that in the notes, but it's the hang time. So this is the range that the ball travels horizontally, and it does it in the hang time. So I'm just going to mark that. And now it travels that distance to xf. If we mark it at the hang time, it travels that distance from 0 to xf at constant velocity. For a position time graph, that is a constant slope. Just like that. Okay? So, the slope equals v sub x, and it's constant for the entire trip. We know that. It's also positive, because it's going up the graph, not down. All right, but how do we show the position in the vertical plane for the same projectile? Well, look at where the ball starts. It starts up here on top of the table, where I would normally take the 0 position to be on the ground. So it starts at a height we'll call y. Sub O, and it ends on the ground. So right here we need to start it up here at 0 seconds, okay? And sometime out here at the hang time, the same hang time that we had over there, it's going to hit the ground because it's coming down. Now here's the catch. We're not going to go from here to here along a straight line because a straight line slope means constant velocity. And we know that in the vertical plane, gravity affects the ball and it has the acceleration due to gravity, which points down. Okay? So it needs to have a negative slope to show that the velocity is increasing downward, but it also needs to be curved, increasing slope so that it shows we're accelerating. So it will do something like this. And end right there. It starts from rest and accelerates downward. So you get a half parabola for the shape of the position time graph. Kind of cool, okay? All right, so those are the positions. All right, now let's take a look. And I'm just going to draw a line across the page because those are the position time graphs. And I'm going to push it up a little bit. Now let's take a look at the velocity time graphs. The actual motion, not where the object is at every point in time, but how fast it's moving at every point in time. All right, so we're going to have a velocity time graph for each side. Okay. So here's our timeline. The origin is right there. And I'm going to go ahead and mark TH, our hang time. Okay. Now, over here, we have the positive horizontal velocities and the negative, although as we know, it only goes one direction horizontally. So we don't have to worry about it going in the negative direction. It just goes to the right, so that's all we have to worry about. However, in the vertical plane, it can go up as well as down, but in our particular case, it only goes down, okay? So here's the vertical or y-plane velocities. All right, now we've got them labeled. Now let's take a look at each one and think about what's happening. First off, we know that the description of the motion in the horizontal or x-plane is that it travels at constant velocity the entire time. And for our little picture, it's traveling to the right, which we can make positive. So I'm going to pick whatever our v sub o x is, our initial x-plane velocity. It stays constant for the entire hang time. Remember, the motion stops at the hang time because that's when it hits the ground and both motions stop. So there we go, constant velocity. The slope is the acceleration in the x-plane, and as you can see, it's 0. There is none. Okay? The area right here would give you the range. It should give you this from 0 to xf. This area, the area should equal x sub f, the range. Okie dokie. Now, let's take a look at the velocity in the y-plane. As you know, the velocity starts from rest because it's not moving vertically when it leaves the table. It has to begin to accelerate down. So the velocity will start it from 0 and increase in the downward direction. Now, these are the downward directed velocities. So we need to start at 0, and by the time we reach the hang time, we are traveling some final velocity in the y-plane. So out here at the hang time, we mark that final velocity. Now, as you know, we're adding increments of negative 9.8 to our velocity every second. So that's why you get 0 plus negative 9.8, then plus another negative 9.8, plus another negative 9.8. So we're increasing our velocity in the negative direction, and we're doing it uniformly in increments of negative 9.8. So our slope should have a value of negative 9.8. It should be a uniform slope to show uniform acceleration. So right here, the slope equals the acceleration in the y-plane, which is negative g, or if you will, negative 9.8 meters per second squared, because it's due to gravity. So that's how we would describe the vertical motion of the ball when it rolls off the table. Starts from rest and uniformly increases to whatever final y velocity it has when it hits the floor in a downward direction. Okay? All right. That takes care of the velocity ones. So now, the last one. Let me shove this up a little bit more, and I'm going to draw another line across the paper. Okay. Now let's talk about the acceleration time graphs. Oh, by the way, I almost forgot. If you look at the area right here between the x-axis and this area gives you this area, all right? It gives you your vertical height that you fell from, okay? That gives you your vertical height. Y, it would be the y sub o up there. 0 to y sub o, this should be equal to y sub o, the height from which you fell, okay? Oh, and there goes my grandfather clock. Just hang on a minute. It's late. Oh well. It's gonna bong a minute or a few seconds here. While we're listening to the bongs, let's do our axes. Well, that didn't take too long. All right, and I'm going to do one for the vertical side. Now remember, we're doing acceleration time now. Okay, so here's time. And if we mark the hang time specifically, all right, we have positive x-directed accelerations and negative ones. And here we have positive y-directed accelerations and negative ones. All right, let's start with the vertical motion. Now, right back up here, we said, look, the velocity is constant. There is no horizontal acceleration. So how would we show that on this graph? For the entire hang time, the acceleration is just 0. Okay? A sub x equals 0. All right? What about the vertical motion? Well, right up here, we just said we have a uniform acceleration increment due to gravity, and it points down, which means we're going to make it negative. So right down here, the acceleration is the value of g, and it's negative. If you wanted to write negative 9.8, that'd be fine too. But it's uniform. The increment stays the same. We're constantly going to add increments of 9.8 in the negative direction. Okay? And there we go. Kind of cool, huh? Now, some of you may be thinking, well, see that the slope is 0, but slope doesn't have any meaning on an acceleration time graph, but the area does. What would be the area? Well, for an acceleration time graph, the area is the change in velocity. So from 0 to the hang time, the area here would equal the, from 0 to negative VF, oops, I forgot the negative on that, 0 to negative VFY. Notice it is a negative area. It's below the x-axis. So we get negative VFY for that one because we started with 0. So VFY minus 0 is just VFY. So that's what that would equal. The change in velocity here from 0 to VFY would be VFY in the negative direction. Okay, and I think that's about it. You are going to find these very, very helpful for your assignment tomorrow. It's a typers on half parabolas, and we must be really good at answering questions about half parabolas because Wednesday we're doing full symmetrical parabolas, and they are much, much more involved than half parabolas. I started with baby steps. Now, guys, well, maybe that's not a good analogy. Okay, I started on the shallow end of the pool. But now, guys, Wednesday, we're jumping in the deep end. So we've got to be able to swim rather than sink. So make sure you understand these graphs. Make sure you do a good job on the typers tomorrow. Okay? Thanks a lot.